right, welcome everybody to week 5, day 3, the very last day of week 5. It's actually day 2, I guess, because we weren't here on Monday. So let us take a look at the triangle testing assignment a little bit. I don't want to put up the answer on here because it's going up on YouTube, and the answers will be there if I choose to use the assignment again next year. I sometimes do, I sometimes don't. I recycle somewhat. But one thing that is important is to realize that floats and doubles have error, right? And so you might want to make a function like this, like called equals ish. It takes like maybe a double F1, double F2, and a double epsilon, epsilon, like that. And so if the absolute value of F1 minus F2 is less than or equal to epsilon epsilon, return true. Otherwise, return false. So this is a way that you can do comparison between doubles that don't require you to not have error in them ever, which is a very dubious and dangerous thing to assume. You can actually probably rewrite this a little bit better like this. Yeah. Okay. That's even simpler. So what we were saying before is if true, return true, if false, return false. So we just return the value. Okay. So this is a equals-ish way of comparing two numbers. So if we go float F1 is equal to read float and Cout equal alpha equals ish F1 F2 0.01, something like that. Okay. Equals ish. It's not a real word anyway. Who cares how it's spelled? Okay, so if we type in 8 and 9, they are not the same. If we type in 8 and 8.1, they're not the same. If we type in 8 and 8.01, they are the same. Okay. So this is generally speaking what you want to do, and you have to control that epsilon so that you pass all the tests. You don't want it to be too accepting or too discriminating. So that's the right way of doing it. Okay. Bool alpha makes it print true or false. If you don't have it there, then rather than printing true and false, 8 and 8 is 1. 8 and 9 is 0. So by default, when you see out a Boolean, it prints out 0 or 1. And if you want it to be words instead, if you want the Booleans to be alphas, you use bool alpha. And then that will print true and false instead of 0 and 1, or 1 and 0. Cool. All right. So let's get started on the topic for today, which is the notion of like really how to start a project. Like how do you, we're going to go over some really big important topics today. We're not learning C++ really today. This isn't C++ exactly. This is an acknowledgement of the fact that floats and doubles have error in them. Every time you do arithmetic, you can accumulate a little bit of error in the last digit. And so you need to be able to handle that, right? So what we're going to learn today is we're going to learn GDB. GDB is the GNU debugger, which is a very important thing, so you can help understand what your code's doing and why it's not working and things like that. I guess we'll also go over Cout debugging, which is the thing. These are two camps. Which one is the big brain camp and which one is the small brain camp? I will leave up to you to decide. I use both. I like I said on a lot of these big divides, like I just really don't stake an opinion on it, you can do either. It's fine. It's your life. Do what works for you, and we'll go into this in a second. And then we're also going to cover top-down programming and what's called bottom-up programming. And so top-down programming means start with main and then write your functions. Bottom-up programming means start with your functions and then write main. Because what you're going to find is in a lot of these programming assignments you're going to get, they get bigger and bigger, you run into like a chicken and the egg problem, right? You can't write main because main requires the functions. So you can't write main first, because if you're calling the functions that don't exist, it won't compile, right? So like, let's say I was doing triangle testing, and so triangle testing is going to require a call to classifier or something like that. So int x equals classifier ABC. Classifier doesn't exist, it won't compile, right? So you're like, okay, well, I have to write classifier first, right? So you come up here and you write your classifier, float A, float B, float C. But then, like, if you're writing this, then how do you test it? Because main's not written yet. And so it's a very common trap that programmers fall into, is that there's this chicken and egg. Like, I can't do main without classifier written. I can't write classifier without main written. So I'm just going to write both of them at the same time, and I'm going to write all of my code, and then I'm going to test it, and nothing's going to work, and I'm going to get very frustrated. Okay, and that's a bad way of coding. Okay, you do not want to code that way. What you want to do is code 4 or 5 lines at a time, and then test it. Okay, and so the question is, which one do you do first? Do you do main first, or do you do classifier first? And how do you solve that chicken and egg problem? So let me show you how to do it using top-down programming first. Okay, so we'll get to bottom up, I guess, next. So with top down, you start by writing main, and you make your functions into stubs. Okay. A stub function does what the function is kind of supposed to do. So if you're making a classifier, we could just, well, what do we have? We have like an enum or something, right? Enum, triangle type or something like that. Something like that, right? And we had like equilateral and isosceles and right, scaling, and error, I think, were the options. So this thing is a triangle type. Okay. And this would be a triangle type here. So right now we're calling a function that's not returning a value. This is something I saw a lot of students have trouble with. They're like, well, I'm just going to write a classifier later. This is actually really horrible, because you promised C++ you're going to return a value and you're not. And this can cause problems up to and including seg faults. And so what you want to do is you want to stub your program out, which means you're going to call classifier and it's going to return a value that's plausible. It's probably wrong, but it's going to give you data to work with. Okay, it's going to give you something to work with. It'll compile. That's the big thing. So we're just going to return, I don't know, scaling. Okay, other, right there. So if we pass the classifier, like 3, 4, 5, then it's going to return, not right, it's going to return scaling. Okay, do you guys understand what we're doing here? We're having a stub function so that we could call it from main, and it's going to give us a value that it feasibly could give us. Like, it's probably going to be wrong, but it could be scaling, like, who knows? And then that allows us to write main. Okay, so we can do like a for loop, and we can like ask questions and do classifications and print things. And in the meantime, we haven't had to actually write classifier yet, but we have all the calls in there. Okay, so now we can like kind of write main a little bit, right? So if x is double equal to equilateral, then cout equilateral. This is isosceles, cout ISO 9000. Right, scaling error. Else cout, this should not be possible. And the reason why it should not be possible is because we're covering all of the possibilities in And so if we made like a copy paste error like this, then that will trigger and it'll say this shouldn't be possible. And you're like, oh, I screwed up. Yeah. Isosceles is right. Scaling error. You are always right. Scaling would be like other people. Error is you done goofed a wrong. And so I've written main, right? And now I can test main. I haven't written classifier yet. I just have a stub. Do you guys see what the purpose is here? Like I'm working on main right now. I'm working on like I'm calling a function. I'm getting a value back. I'm going to print a thing. Now I need to test it to make sure this is right. Because every time you write code, you need to make sure don't other people. Okay, maybe I'll just make this. There we go. For something. Okay. Okay. So good, it worked. But let's say that I screwed up my my thing here, right? I did a copy paste error. I had an isosceles in here. Copy paste error, right? Happens. Then not you. G++. And this should not be possible. Oh, this should not be possible means I screwed up as the programmer. Okay, because these are the only possible answers when you have an enum. An enum is essentially 5 constant integers, one called equilateral, whose value is 0, one called isosceles, whose value is 1, one called right, whose value is 2, one called scaling, whose value is 3, and one called error, whose value is 4. This should be covering all of the possibilities. But anytime I'm working with enums like this, I always have this little else statement here for 2 reasons. One, I could have a copy-paste error like this where I put isosceles in twice, and I screwed up, right? And that's why you test your code, to find these things, right? And so I've got, okay. Scaling. All right. Oh, wait. Yeah. Okay, good. But the other problem is, like, what if we add in another, another case here, right? Like a queued and obtuse angle, that kind of stuff. If I don't update my code down there and I return like obtuse, then I get this should not be possible. Okay, and so this is a way of coding so that even if in the future I add more types, my code will detect it, and that in reality is not going to just print this should not be possible. That would actually kill my program. Usually, I would usually be like, I would normally do something like this: assert false. An enum in triangle type was encountered that doesn't exist. Okay. And so assert is like the pro gamer way of doing die. Right? You've all seen, in your homework, if you get an error, you print bad input or error and quit. Right? Assert is like the pro gamer version of that. Does it not take a parameter? Too many arguments. Fine. We'll just do this. Okay. Assert false. Okay. So now, if our code's running, it will actually kill our program and tell us which line of code our thing died on. And then I can look at this and be like, encountered an enum that doesn't exist. Now you might think, well, if you add a new type, like acute or whatever, like why wouldn't you just come down here and change it down here? Here's the thing. In real life, code has millions of lines. In real life, when you're working on a code base, there are going to be millions and millions of lines of code, and you are not going to remember every place where this thing shows up, and you added a new thing here. These kinds of things might be in 10 different files, and you might not remember all of them. And so every time I write something like this, where I'm checking all the values of an enum, I always have an else that checks for there being something new in the enum that I forgot or to put in here. Okay. And so if this ever comes up, it kills my code. It kills my code dead. Now for you guys, you could have deleted that. it wouldn't have mattered, right? Because none of the test cases could possibly trigger it, because this is you screwing up. But I always have basically something like this. So yeah, an enum is exactly the same as if I've written constant equilateral equals 0. See how it's getting mad at me? Constant isosceles equals 1. See how it's mad at me? Constant right equals 2. Constant 3, and so on and so forth. So you see how it's mad at me? It's a redefinition of it, because the enum basically does all of this stuff for you just with a lot less typing. Okay. So it creates a series of constants. The first one's value is 0. The next one's value is 1, and so on and so forth. So it guarantees none of them have the same value. They're all constants. It just makes life easy. And if you return, it does something even better than that, because I'm not returning an integer, right? I'm returning a triangle type. And so if I return like a 42 here, it gets mad at me. You see that? Because that's not part of the triangle type, right? So the only things I can return from the classifier are things that are on my list. So I could return a cube or something like that, right? But I can't return, whereas if I had a bunch of constants, then I would be returning an int. And if somebody returned negative 9,000, like the compiler can't check for that. So enums are really nice when you have a fixed list of options like this, and you basically make a constant for each one of them, and then you refer to it as right instead of the number 3, which doesn't mean anything to people. You could return 3. No, it's not a triangle type. Now you could cast it triangle type. This should work. Yeah. And so this will return scaling. It's just a garbage equivalent of return scaling. Right? You guys see the difference here? That's a number that doesn't mean anything to the human. That's a word that means something to the human. If I'm returning scaling, I can read it and know that it's a scaling triangle. Whereas if you return the number 3, nobody knows what the hell that is. And they have to go up and like double check and start counting. Like, okay, that's 0, that's 1, that's 2, that's 3. And even worse, if you ever reorder these things, right? Like, I'm going to alphabetize these things, right? Come over here and start alphabetizing and stuff like that. Now you're not returning scaling at all. You're returning a obtuse triangle now. Do you see why? You never want to use things like this. Like, this is just a very, very bad way of doing coding, because returning 3 only makes sense if like you're returning a number, right? Like, you're adding 2 numbers, you get 3. Like if you're returning a triangle, you should just return, use the words. That's code is for humans, and so you want to be clear that you're returning an obtuse triangle, not 4 or 3 in this case, Okay. So returning 3 is the same thing as returning obtuse, but it's better. Because again, if you move the things around, you don't have to update the values, it's more human readable, et cetera, et cetera. So enums are just better than, like I could have done this whole assignment, like, return an int, right? And then and this would work, right? This works fine. It's because these things are all just ints. That's fine, but it's garbage, right? Because it no longer is limited to just the options on the table here. I could return negative 9,000, right? That's fine. It's an int. Do you see the benefit that enums give you? Like, it prevents you from returning things that aren't on the list. If it's a triangle type, it has to be on the list. If it's on the list, you can't return it. You can't return negative 9,000. Even though they're ints, it's not on the list. And so the compiler detects it and it's like, no, you screwed up. Okay. So this is how we do it. Okay. So and so this is gonna kill our program. Okay. So right. Okay. So let me get rid of obtuse and acute because that's on the homework. And let's talk about this. Okay. Isosceles. ISO-CLES. Okay. So I've written main, and I can actually just change the value that is being returned by the classifier and just make sure that my code in main is working correctly, right? Cool. All right. So I've written this code in main. I'm now happy that I've covered all the test cases. All right. Now I might do the input. Let's see here. Float a equals 0, equals 0, equals 0. I've seen a lot of you not initialize your variables. I've seen a lot of this. Don't be this person. Be this person. Okay. Cn into A, into B, into C. And then every time you cn something, you need to do what? Especially when you're seeing in like an integer or something like that, or there's large numbers of squirrels and declarations of independence running around. What's the first thing you should do every time you cn into an integer? Yep. Yep. Yeah, you got to vet it, right? Make sure that what was typed in is valid. So if not cn, die or something, right? Right. So I usually have something like this in my homework, so that if the user types in something wrong, it'll die. Okay. Now, this code here is bad. It's not returning anything. So again, we should return scans. So that's the whole point of a stub. The whole point of a stub is that it allows us to compile our code, which is the most important thing, so we can test it. You can't test your code if it doesn't compile, right? So it allows us to compile our code, and it also gives us a value that's reasonable. Like if I was making like a blackjack or a craps or something like that, and I was doing top-down programming, I'd be working in main. I might call into like a random dice roller or something like that, and I haven't written it yet, and so I just stub it out. I just have the random dice roller return 5. It's a value that could be returned, right? I'm not returning 100. I'm not returning -3. I'm returning a value that plausibly could be returned. And just every time I roll the dice, I get 5. It's like, okay, cool. Do you guys understand? Like the notion of a stub. It's one line of code, return 5, and then it's done. Main's happy. It's happy. Everyone's happy. It's not very random, but like it gives you a number. Like give me a random number, 5. Here you go. It's random. I picked it randomly. It's a random number. So a bad habit from Zybooks. Yeah, I know. It's an issue I have with Zybooks. So Zybooks teaches you to write code this way, but don't write code that way. Trust me on this. In the last week alone, I had at least 4 or 5 students have bugs in their code because they did this, right? They didn't think that the numbers would be used uninitialized, but they're being used uninitialized. So just have it. Just always initialize your instant floats to 0. Okay, so does that notion of a stub, this is a stub, right? It returns a wrong answer, but it's a plausible answer. That makes sense? You want an error for bad inputs? Yeah. I mean, I'm not going to redo the homework right now, but sure. Okay. So, all right. So now that we've got main pretty much done, we're going to come in here and work on the classifier. Okay. And the first thing you typically do, which I'll just leave that in. The first thing you typically do when you have a function is you make sure the variables passed in are correct. Some people were putting in the if not cn up here. Don't do that. The function itself doesn't do any cnning. It doesn't read from the keyboard. So it shouldn't be checking to see if there's an error in the keyboard. It's not its job. Okay? It's the job of whoever it is that reads from the keyboard to see if there was an error reading from the keyboard. So down here, that's where it should be. This should not exist in the classifier unless the classifier was doing the input, which it should not be. Okay. But there are some ways that things could be bad. So for example, we could say if A or B or C is less than 0, then return error. Okay. And otherwise return scan. So let's test this. Let's see if this works. Okay. So 2, 2, 3. Uh-oh, that's an error. -1, -1, -1. Okay, that one's correct. 0, 0, 0. That one's correct. So why am I getting 0, 0, 1? Why am I getting errors on all of these things, right? What's going on here? Why is 1, 1, 1 an error. Okay, so the problem lies in the fact that your English brain and your computer science brain aren't the same. Okay, so in English you would say if A or B or C is less than 0. And this, unfortunately, is valid C++. It's not valid Java, probably for this reason. But it's valid C++. Because if you remember, A is true when it's not 0, right? So yeah, if you want to debug this, anytime you have a complex if statement, you can always split it into multiple if statements. Okay, and so like, okay, this code's not working right, and we could do something like this, like cout hi. This is called cout debugging, right? Okay, and then if we get to here, we'll print out hi to I don't know, and then 333, and it doesn't print out hi to. Oh shoot. Okay, so the problem is somewhere in this line, but your English brain will look at it and be like, it looks fine to me. So here's trick number 1. Trick number 1 is, so this is learning point. This is another learning point, top down for me. We haven't done bottom up yet, but okay. So you can always split an if statement. Okay, so I could rewrite this if statement like this. If A, return error. If B, return error. If C is less than 0, return error. Okay? And now that I've done that, I can scatter my couts throughout the code and see how far we get. Okay? So if I type in 111, oh, the very first one. Okay, so we got here, but we did not get here. So that means that line right there was returning error. And I wasn't expecting it to, right? So what's going on here? Why is it returning error if A is 1, right? And so that helps you identify the problem, right? A is true for all values except 0, right? So if I were to type in 0, 0, 0, actually it's a floating point number, isn't it? So yeah, who knows? It's not even an int. So yeah, it's just going to return error every time. Okay. So what we wanted to say was if A is less than, or yeah, let's say less than 0. Okay. And B is less than 0. So we're going to fix that, right? And now if we type in 0, 0, 0, it gets all the way through and prints other. But wait, 0, 0, 0 is supposed to be an error too, isn't it? I mean, 1, 1, 1 is fine. -1, -1, -1. Interesting. Interesting. What's going on here? Because we're not passing in A, B, and C. You see that? And so one of the things that I was going to do next is I would cout A and B and C, right? Because this is not behaving the way that I expected it would, right? So if your little stupid hi to things aren't working, then I pass in 1, 1, 1, then, oh, yeah, we're not getting 1, 1, 1 at all, right? We forgot to do that in main. This is how, this is why this is not especially useful, right? It's actually better to do this, right? So now if we change it back here, we have discovered what the problem is. We were hard coding which numbers get passed in the function. It's 3, 4, 5. Okay, so we pass in 0, 0, 0. Okay. And if we pass in -1, -1, -1, then it gets to here. It does not get to here. Therefore, it is returning error successfully. Cool. But if we pass in 0, it prints out hi, hi 2, hi 3, hi 4, and returns other. And so then we go like, yeah, well, 0 should be a problem too. So we change that and that. That, and it works, and it works. See, it got to here. Okay, so that's called cout debugging. You just cout all the things. Okay, so cout debugging, you cout all the things, or even better, error all the things. Error is like cout, but is not looked at by the auto grader. Okay. So a lot of students get into trouble because they see out all the things and then they forget to pull them out prior to turning it in. And so the auto grader like looks at their output and be like, yeah, that's wrong. Right? So see error, anything you see error will appear on the screen. Watch, it's going to be exactly the same as what we had before. 0, 0, 0, 0, 0, hi, you done goofed, run, 1, 1, 1, hi, how's other people, right? It's exact same output. However, it's actually being written to something called the standard error and not the standard out. And so that means the auto grader will actually discard everything that goes to the standard error. So this is safer, okay? So if you happen to accidentally leave this into your code, when the auto grader runs, it doesn't count against you, okay? So anytime you're doing this kind of like logging stuff or like cout debugging, just use error instead of cout, and it's safer. Now that we've gotten all this done, I can pull the couts out, right? That one I might comment in case I need it again later. And then I'm going to reassemble these if statements back into one if statement. So I'm going to basically say if A is less than or equal to 0, and or B is less than or equal to 0, or C is less than or equal to 0, and we're good. So this was our original, this is our fixed. So that is how you can debug an if statement. You split it. Well, what if the if statement has ands instead of ors? With an or, you go if statement, if statement, if statement. With an and, it's a little bit different. So let's say we have if A is equal to B is equal to, and B is equal to C. Okay? Or, yeah, let's say this one. Okay? Then return isosceles. Okay? So, right? Because we got two sides that are the same, right? That's what we're saying here. No? What kind of triangle actually is this? If A equals B and B equals C, which kind of triangle is it? Yeah, it's an equilateral. But we're doing bad code, right? So if you have an and that you need to split, it looks a little bit different. You split it like this. If A equals B, and if B equals C. So ors become like parallel if statements, and ands become nested if statements, right? And so this if statement here only runs if this one was true. And so it's like an and, right? And so then we can see out, hi, and I2. I wouldn't actually debug this way, but and we can return isosceles. Okay. Okay. So we can use this to. So I typed in a 334, which should be isosceles, right? But instead it's returning other, and it's not getting to high 2. So the problem, lies between here and here, right? So, why? Oh, shoot. Yeah, that's 3 and 4. So that's not isosceles. Yeah. So that's how you bracket your bugs. Okay. So you scatter cout statements everywhere, and you use them to bracket the bugs and figure out exactly where and why you're going wrong. Okay. Now let me show you a perhaps better way of debugging. It's arguably better. It's arguably worse. So our solution here was to change that to equilateral, and then if we want to combine it back into an if statement, then we can combine it back. So you split it apart, you debug it, and you can smash it back together. Okay? You guys understand that method? So if statements can be very hard to debug. If there's 50 different things going on, it can be very hard to be like, all right, which one of the ors or ands or nots is actually causing the problem. Okay? And so if you want, you can split. Any if statement can be split up this way. Okay? A not can be turned into an else. Do you guys understand that method? It's a pretty powerful method of debugging. Like, you can break your complicated stuff into simple stuff and then debug the simple stuff. Okay. So this becomes if a is less than or equal to 0. Right. And so an OR can be split up like this, and an if you split up like that. Okay. So that's an AND, that's an OR. They're logically the same. Now, let's say that I want to make my triangle testing code simpler by sorting the three elements. So we've got A, we got B, we got C. And rather, because a lot of students, their code got really kind of gnarly. They're like doing hypot between these two and this one, and these two and this one, and these two and this one. And for the sides being too long and too short, they were comparing every possible combination of side. And there's an easier way of doing it, which is to sort the three things. So you can say if like A is greater than B, then swap A and B, right? So if you get like 3, 4, 5, it'll be fine. But if it's 4, 3, 5, it'll become 3, 4, 5. And then if A is greater than C, swap A and C. And if B is greater than C, swap B and C. And so if I want to see if this code is correct, I will put in I'll put in a CR statement before and after. You guys see that? So I'm going to print out A, B, and C first. I'm going to try and run this code, see if it works, and then print it out afterwards and see if it is, in fact, sorting them least to greatest. Okay? So 10, 5, 20 becomes 5, 10, 20. Cool, it worked. But we got to try every combination, right? 1, 2, 3 becomes 1, 2, 3. 3, 2, 1 becomes 1, 2, 3. 2, 1, 3 becomes 1, 2, 3. 3, 1, 2 becomes 1, 2, 3. Okay, so it's working. Like basically, we're going to test all 6 combinations, and then once you're confident, because you tried every possible combination, then you just put in a comment here saying sorts A, B, and C least to greatest. Because anytime you have something like that that's kind of weird looking, you need to explain what you're doing. It's the WTF principle. Okay. Anytime somebody looks at your code and goes WTF, that's a sign you need a comment there explaining what the hell you're doing. Okay. WTF. Do you guys know what it stands for? Like, I don't want to, like offend you or anything. Like, do you know what WTF stands for? It stands for the World Taekwondo Federation. So, World Taekwondo used to be called the World Taekwondo Federation until a few years ago. It was renamed to avoid the negative connotations of the previously used WTF. I walked into my dojo and I'm like, they changed the name of it finally. I always thought it was kind of funny that what kind of Taekwondo do you do? I do WTF Taekwondo. So WTF stands for World Taekwondo Federation. Okay. So yeah, anytime somebody looks at your code and says WTF, you probably should have a comment there explaining what you're doing. That's how you should comment your code. You should explain why you're doing this. Okay, what it's doing. Okay, why it's doing it. All right. So there we go. Okay. Now let me show you a different way of debugging this. Okay. And let me add in. Take this out. I guess you understand it all now. You all understand it. Let me add in another check. So now that I know that A and B are the small ones and C is the big one, I only have to do one check to see if it's valid, not 3. Okay, so if A plus B is less than or equal to C. Return error. Okay. So I don't have to do 3 checks now. I only have to do 1. Now, let's see if this code works. Okay. So I'm going to type in 000. That's an error. 111, equilateral. What about 11100? You done goofed. All right. I mean, everything's looking good so far. Let's add in isosceles here. When I'm typing at a weird angle, so I'm always like off my keystrokes. Okay, so if we do a 11100, that's an isosceles. Wait, no, that's not right. It's supposed to be an error. What's going on here? Okay, so let me show you the other way of debugging. So the other way of debugging requires you to compile your code with the -G flag, or you can use compile. It does it for you. Compile main.cc. And then we're going to run what's called GDB. GDB is the GNU debugger. It was written by my boy, Richard Stallman. Richard Stallman is one of the most important people in computer science, up there with Bill Gates, Steve Jobs, Linus Torvalds, and things like that. He came out here a few years ago and stayed at my house. It's kind of nice. So we're going to GDB a.out. And what that's going to do, it's going to load the debugger. And so my program is loaded inside of the debugger. Okay, and so what do I do? Well, that's what we're learning today. So the first thing you do is you just run your code and type in, I don't know, 345, and it returns, and you're done. You're like, all right, well, that didn't really accomplish anything. So let me give you how GNU debugging works. Okay, so step 1 is compile your code with either compile the shell script that I wrote for you using easy peasy, or G++-G, and that backslash there means don't use any aliases, because by default I have an alias set up on G++ that turns on the optimizer, and the optimizer will delete code, which isn't good when you're debugging your code, because there's lines of code that are now missing because the compiler deleted them. So if you compile your code with backslash G++, and then with the -G flag, that turns on debugging, then you will get debug information. Or you can just unalias G++. Okay, so compile your code, ++-G, and then step 2 is GDB a.out. Okay, so step 2, load your program inside of the GNU debugger, like this, GDB a.out. Step 3 is you need to set a breakpoint, which means it will stop when it gets there. You can either breakpoint like, let's see, what line number is this? Line 29. You guys see down there at the bottom right corner of the screen, it tells you the line number. Or you can set new, and that shows line numbers. Either way works just fine. You get the line number that you want to break on, and so you can either do this, break on line 30 or something, or you can type in the name of a function. So you can break on classifier, and then when it gets to the classifier function, it stops there. The second way is probably a little bit easier, but also maybe a little bit more typing. It's up to you. And so after you set a breakpoint, then you run your program. Step 1. Okay. And then your program runs as normal, but once it hits your breakpoint, it stops. And you can examine the variables and stuff. Okay. Let me make one change here. GDB-2e makes the code look a little bit better. Makes the debugger look a little bit better for you. Okay. So G++ main.cc. Oops. With -G flag. Then GDB-2e a.out is going to run the 2e version of GDB. You can switch between the two of them if you want. There's 2e mode, there's text mode. You know, if you're starting off, probably 2e mode is better. I don't know. And so we can set a breakpoint on line 33, and you'll see a breakpoint appears right here. And then when we hit run, the program just starts running. And so right now, we're presumably waiting on our input. So I'm going to type in 3, 4, 5, and then it runs and it runs and it runs until it gets to our breakpoint, and then it stops. And so you can see right here, it says we are on line 33 of main.cc. We're in the function called classifier. The value of A is 3, the value of B is 4, the value of C is 5. Okay? And so if we want to step through our code, we can do so. And there's 2 different ways you can step through your code. You can step over a function, or you can step into a function. So do you want to see the source code for swap? I don't. So I want to step over it. And I do so by typing next. And that just goes to the next line of code. I don't want to go into the function call for swap. I don't care. I am pretty sure the standard library swap code works fine. And so now I can print the value of A. The value of A is 3. You print the value of B. The value of B is 4. You print the value of C. It's 5. So I can examine all of the values of the variables here and go to the next line, go to the next line, and I can print out the value of A. And so John Carmack, who's one of my personal heroes, he says every time he writes code, he immediately loads it up in the debugger and runs through it and steps through it one line at a time and sees if it's doing what he thought he was doing. He says a lot of people have an idea in their heads of how their code's supposed to run, but a lot of times the model in their head is wrong. You know, the computer in front of you is better than the computer in your head. So if John Carmack steps through his code to make sure that it works right, maybe you should too, I don't know. Or you just see out all the things. It's up to you. I don't have a strong opinion on that. So we come here, we hit next, and we can always print the values. Print A, print B, print C. So A is 3, B is 4, C is 5. Okay, so the two of them are not the same. Okay, so we go to the next one. And we go to the next one, we go here, and then it returns back out, and then it goes here, and then it's a scaling, so it prints all those other people, and then it quits. Okay, cool. So everything seems fine, right? But that wasn't the problem. The problem was like we were having an error input, but it wasn't outputting the error for some of the test cases. So let's launch it again, okay? And I'll set a breakpoint on classifier. Okay, I'm gonna run it, and I'm gonna type in 1,000 or 10,000, whatever. Okay, and so I can step over. I'm just hitting N. If you keep hitting return, by the way, it'll just keep doing the same things. Come here, and then oh look, we returned before we got to the check where we were checking for the error. Oh, because 10,000 is oh. Do you see? You see how that works? You can step through your code, and otherwise you're just like, it's returning error. I don't know why. And you know, a lot of you had like different checks for error, right? Like, so you would have, you know, a check for error here, and a check for error here, and you don't know which one is triggering, right? Which one of these is causing the thing to say it's an error, you know? And so by going to the debugger, you can go through it a line at a time. You'd be like, oh, it just answered isosceles. That shouldn't have been isosceles. I need to check for the sides being wrong before I check for isosceles. For equilateral, I don't think it matters. Because equilateral 333, like it should be fine. But for isosceles, yeah, we need to bump that check up a line or two. Okay? So that's called Gdb debugging, all right? And so you run it, and then it runs until the breakpoint. Okay, and so print A, prints the value of the variable A. Next goes to the next line. Steps into the function. I haven't shown you that yet. I can show you that in a second. And then backtrace shows you the call stack, which we'll learn more about later. Up takes you back up the function level. It's pretty good for now. Okay, so let me show you what that looks like. So I'm just going to launch it again, and I'm going to break on line 38 or whatever. Break on line 38. Okay. And so I'm going to run, and I'm going to type in, I don't know, 10, 10, 20. Yeah, whatever. Okay. So we got a break. Go to the next line. Now, let me show you what step does. So step goes to the next line of code inside of that function call. So it's going to step into the function. Oh, it got deleted, didn't it? Lord. Okay. Let's do this instead. So float hypo equals hypot of A and B. And then we can say like if hypo C return right. Okay. Hypot doesn't exist, so let's go up here and put in C math to make it exist. And we will do the last compile and last GB. And we will break on line 43, I guess, and run. 3, 4, 5. Okay, so here we are. So we've run our program, it's gone to this line of code, and it stops. And we can print out the values, make sure they're all what they say they are. We got A, B, and C. Okay, everything's cool. So if you want to see inside of Hypot, you can do what's called step. And it takes you into the standard library. So you are not in Kansas anymore. You are now in code that you did not write. This is standard library code. And standard library code looks bad. So I don't know why this is their coding style, but it looks like they just love themselves some underscores, underscore X, underscore Y. Why you couldn't call that X and Y, I don't know. It doesn't make the slightest difference to anything, but there you go. And so this is what the standard library looks like, and it is not a good looking bit of code, in my opinion. So, yeah, and so you can hit next or step. And now it's stepped into some code that we don't even have source code for. So now we're like lost in space, okay? And if you want to know like where the hell am I, you can type backtrace, okay? Or BT for short, same thing. And you can see what's called the call stack. And so the call stack is like what functions have called which functions, which have called which functions, which have called which functions to get where we are today, okay? So main called classifier, and classifier called hypot, and hypot called this function called hypot f underscore hypot f, in a file called whypot f underscore compat.c. We don't have the source code for it, so but that's where we are. Okay, so we were on line 59. That's what the colon 59 means. We were on line 59 of main.cc when we called classifier, and then we went up into classifier. A is 3, B is 4, C is 5. So that's classifier. We were on line 43 of main.cc when we called hypot. And so hypot is inside of the file called cmath. And we were on line 1459 of cmath when we called this function. And so you can see every line of code that you were on when function A called function B, which called function C, which called function D. You can see every line of code and every source code file that you were in when this called this, which called this, which called this. You guys understand? It's very useful to find out that information. Because you got all your variables. Hypot was passed 3 and 4. Classifier was passed 3, 4, and 5. Is that you guys understand? Like that's it's very useful to know where you are. And we're about to do a little bit of recursion, and backtrace becomes a lot more useful when you do recursion as well. You guys with me on this? Okay. So this shows you where you are in your code, up the call chain. Now, if you want to go back up, because we're lost in space at this point, you can type up, and then that takes you back up a level. And I'm like, I don't want to see the standard library code anymore. It's scary. Piece me out of here. Up again. And so if you type up, it takes you up back out of the function. So if you accidentally step into a function, you're like, whoa, that's scary. You just type up, and you're like, all right, we're just going to close that door and not look inside the standard library anymore. Because, I have no idea what's going on. So if you ever step into a standard library function, just type up and you're out. You're back in your thing here. And now you can type next. Okay. And where are we now? BT. Right, because we're inside of BT. Right. So next, right? Next, okay, there we go. Okay, next, there we go, and we're back. All right. So and so now we can print the value of hypo and 5. Okay, cool. And so this might be where, boss, you were saying like you had issues with the numbers not being exactly right. This would show you got two numbers that are very close to each other but aren't exactly the same. And so if you did floats instead of doubles, that was an easy way of getting a lot of test cases wrong because you needed more precision for some of them. So how do you get back to Kansas? Yeah, you can. Yeah. So. Yeah, and so you just look at the value of hypo, look at the value of C. You're like, oh, they're very close, but they're not the same. Must be rounding error. So, yeah, all right. So quit, and then you run it and you test it with -3, -4, -5. Yeah. So maybe. Maybe this is in the wrong place. I don't know. But this is the process, okay? So you write a little bit of code, you test it. You write a little bit of code, you test it. Okay, don't write all of main and all of your code all at the same time. It is a recipe for disaster. Just, if you've added a test for right triangles, test it. Okay, don't move on to isosceles. You know what I mean? Make sure you test right triangles and make sure that it works with every form of right triangle. 3, 4, 5. A 6, 10, 8, right? Test the hell out of it, okay? Before you move on. So you have to think of coding like how oysters make pearls, right? They get a little bit of sand in them, a little bit of irritant, and they spit on it, right? And they work on it, and they work on it, and they work on it, covering it in spit over and over again until you end up with a finished homework product, okay? So the homework is the irritant, and the spit, I don't know, is your effort, and then your homework is the pearl. Yeah, there we go. Okay. Right, so you just keep working on it a little bit at a time, adding layer after layer to your code, and then you end up with a beautiful pearl. Okay, even though the whole thing is irritating. So comments, questions, I think covering all the things here. Collateral, yeah, I think that's basically it. That's the homework assignment. Something like that. Questions about GDB? The notes are up in the public. So copy CC public. CP. Actually, didn't need to type main twice. So if you want to view the file, vim, or just make a copy of it, public main.cc into your home directory named awesome attorney is awesome.cc. Something like that. And then you will have a copy of it. So if you want to see the GDB commands, there is all the GDB commands. They're all in that thing right there. And GDB is a tool that is not small. It is a massively big and complicated tool. These are the basics though. Okay. And so basically you write some code, you set a breakpoint, you run to it, step through your code, see if everything's working the way you should, and you can actually see your code running instead of just having some mental model that doesn't match, what it's doing. It's returning error. I don't know why. That's not good enough. So CI debugging, Gdb debugging, either way, you need to learn the techniques to find out what's wrong with your code. That's a core skill in computer science. Is you write code, it doesn't work. Why? You need to be able to answer that question. I'm here to help you, and Mencarelli is here to help you. We're all here to help you. But that's one of those skills that gets built through experience, but also knowing what to do. These are two different approaches. CI debugging, GNU debugging, Gdb debugging are two different approaches that work really well. So, yeah, it's good enough for now. Good enough for now. It can also be used to load core dump files. There's a lot of stuff it does, but it's good enough for now. Okay, so bottom-up programming looks a little bit different. So bottom-up programming, you start with a function, then you write main. And so main, let me show you what it would look like if you're doing bottom-up programming. It would look something like this. If you're doing bottom-up, you would be writing your classifier, building test cases and things like that. And then main would just look like this. And this is something called a driver. So driver is just a main that's like 1 or 2 lines of code, and all it does is it just calls your function and passes some values. Your thing does the thing and outputs the result or whatever. You understand? So there's no, you're not writing World of Warcraft. Your main is just, it just calls your function, passing some values. Maybe you like seeing, maybe you do, something like this. Maybe you do something like this. Like you read some input, you pass it in, print out the result. And then you work on another function, you just switch, switch function name to be like, whatever other function you're working on, and you test the hell out of that. And so what you do is you work on each function one at a time. And once you get all your functions working, and you solve the chicken and the egg problem by just having main, main is nothing, right? You don't have to do both main and classifier at the same time. You work on classifier first. So all main does is it just calls your function. And so this is called a driver. A driver is a very short main that just calls your function, passes some values to it, and then you can test your function thoroughly. Okay. And then after you finish one function, you do another function. Once all your functions done, then you do main, and main is good to go because all your functions work and exist. And then you can you finish by doing this, right? This part here would be last if you're doing bottom-up programming. With bottom-up programming, you write all your functions first, then you do main. With top-down, you write main first with stubs, and you call into all these stub functions. They don't really exist very much, but they exist enough that they compile and they return like values that are like plausible. And both of these ways you should do. You should get practice doing both of them, because you'll kind of figure out for yourself which one makes more sense to you and which one feels better, and you should just get experience doing projects both ways. I typically do top-down programming. I like to get my main kind of set, and then I'll dig into one function, and then that function's function, that function's function, and then kind of build it out, and then move on to the next part of main. It's kind of the way I approach it. But I'll do both. It just kind of depends on the individual project. Sometimes it makes sense to just, like if I'm working on like a 3D game or something like that, a lot of times it makes sense to have your functions ready first. So like if you're doing like a lot of linear algebra and stuff like that in your video games to do rotations and translations and scales, a lot of times like you just want to get all of your linear algebra stuff done. So you have like a working linear algebra library that allows you to move things and rotate them and collide and all that kind of stuff. So I kind of will work on like the pieces first, and then I'll work on the game once I know the pieces work. So it just kind of depends. It's one of those things that just, you develop an intuition from practice, from just like doing it a lot. And you kind of like, and there's no right or wrong answer to you, but like there kind of is. Kind of is. Like, some ways will take longer than others. Okay. So for this one, for triangle testing, I wrote it top down. I did top down for that. Start with main, and then I did main first, and then I slowly built out the classifier just like I showed you today, where I would add a new case for like isosceles or equilateral or something. I would test it, then I'd add another case to classifier, test it, and yeah. So I start with main, and then classifier built up over time, and then I was done. Okay, so next big topic for today, and then we're going to do lab time, is recursion. Okay, so we're going to start with a fresh main.cc, and we're going to talk about recursion. Okay, so recursion is when a function calls itself. Anytime a problem exhibits self-similarity, you can use recursion to solve it. For example, factorial, right? So like 5 factorial is equal to 5 times 4. You guys know this, right? 3 times 2 times 1, right? You guys know how to scream at people in math? Yes? You guys have seen this before? No? Okay, so factorial is, 10 factorial is defined as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's all the numbers from 1 to n all multiplied together. And so what's interesting about factorial is you could do this with a for loop or something, right? But you can define factorial in terms of itself. So factorial is equal, like 5 factorial is equal to 5 times 4 factorial. Okay, so it's self-similar. You can define it in terms of itself. Okay. The only other thing you need to define is when it stops. And so it stops when 1 factorial equals 0. Okay. So if you pass in 1, you return, So if you pass in 1 factorial, you return 1. Otherwise, you return n times n minus 1. And so there's always two things with recursion. You have the stopping point, called the base case, and you have the movement to the stopping point, called the inductive step. So if we were going to write factorial, then let's see here, see out. Okay, so we're going to pass in a number. Like 5, we're going to read a number 5 from the keyboard, then we'll compute 5 factorial, which should be like 120, right? 5 times 4 times 3 times 2, right? It's 120. Okay. So let me write a sample factorial, and you can tell me if it's good or not. So if we pass in 5, it'll return 5 times the factorial of 4. Right? How many people think this is correct? Does it look good? How many times is this thing going to run? I can tell you, those of you that are saying it's going to run infinitely are wrong, probably. It is not going to run infinitely. Once. Nope, it's not once. It's more than 1, it's less than infinity. 5 times? So if you pass in 5, it'll run 5 times? Nope, that's also wrong. It's also not 4, it's also not 6. Zero? Nope. None? Nope. It's not 0, it's not 1, it's not x minus 1, it's not x plus 1, it's not infinity. Less than the value in one number. That's also wrong. It is more than the value. It will run about 250,000 times. What? Let's compile it and find out. All right. Enter the number to factorial 10. Segfault core dot. Huh? What? crash, we got what's called a stack overflow. Let's just print out the value of x here, right? Let's print out the value of x and see what's going on, okay? So let's run it and pipe the results through less, which will show one page at a time, okay? So we're going to enter a number to factorial 10, okay? So we get the factorial of 10, and 10 is equal to 10 times the factorial of 9. Well, what's factorial of 9? Well, it's 9 times factorial of 8. What's factorial of 8? 8 times factorial of 7. And what's factorial of 1? 1 times factorial of 0. What's it? 0 times factorial of negative 1. It's a negative 2. What? Oops. So Alessandra is probably like, oh, but it is running forever, right? It's running forever. Forever and ever, right? Except it's not, because it gets to the end and dies. How does it get to the end? How does that even make sense? Every time a function calls itself, it needs a little bit of memory to remember the state of the previous function call. So there I said, like about 250,000 times. It'll run until it crashes. And so eventually it runs out of memory. And then it dies from what's called a stack overflow. There's a limited amount of stack space, which is the memory used to hold function calls and variables and things like that. And it runs out of it and it dies. Okay, so how do we fix this? Which one of the two things here is missing? Are we missing the base case or are we missing the inductive stub? What do you think? The base case is missing. Okay. So what we need to do is say, if, what do I say? Like if, what do we define as? If the factorial of 1, okay. So if x is equal to 1, return 1. What do you think? We good now? Is this factorial? Is it correct? Won't run infinitely anymore. No? All right. What's wrong? What's wrong with it? Which numbers will cause our code to fail? I will tell you, we still have some stack overflows in here. There's a couple I can think of. Negatives, yeah. So whenever I write code like this, I will typically make a less than or equal to 1. Then it just handles all the negative numbers. Because a lot of students forget that negative numbers exist. And so if we had this code here, it'll work properly if you type in like 5, it computes 120, cool. But if we type in -1, then it runs forever until it's segfaults, right? I don't like writing code that's segfaults. Now, some professors say, well, it's the fault of the person who typed in -1. It's their fault your code crashed. And I say, no. If your code crashes, you're a bad programmer, and you should feel bad and ashamed and like put on the cone of shame, okay? You should never write code that crashes, especially not code that stack overflows like this. So a very simple change would just be to do that. And so if they typed in -50, you return 1. Maybe a more proper way would be to assert that x is greater than 0, something like that. And so what that would do is, that's the, remember I told you earlier, that's like the professional way of doing die. So if they type in 10, it works. If they type in -10, assertion failed. The number you typed in was not, the number you typed in was not greater than 0. And it kills your program immediately. So that's kind of the pro gamer way of doing it. I probably wouldn't even use an assert. I'd probably print an error message to the screen and handle it more properly than just killing my program. But this is good enough. This is good enough for now. So, all right. So is our code good now? Are we handled properly? It could skip over 1 completely. I don't think it can because it's going down by 1 at a time, right? So if you have 5, you can go 5, 4, 3, 2, 1. If these were floats, yes, absolutely. If you're starting at 100 and counting down by 1s on floats, by the time you get to 1, there's a chance that there's error, and it skips right past it, right? So, are we good? Looks good to you, but you're often wrong. All right. Well, what if I just try, like, I don't know, 270,000? Segfault. right? Because a function can only call itself about 250,000 times. And so, and that's not even that big a number, right? 270,000 is not that big a number. You try computing it, boom, code crashes. Okay. So, so maybe what's the biggest value we should allow here? What do you think? What's the biggest value that this code will work for? Just off the cuff, what do you think we should put in here? So we're going to assert that x is greater than 0 and that x is less than, like, maybe 270,000, 250,000, maybe. What do you think? 250? So we think the code's going to work right between about that range. Maybe we tighten it down a little, you know. We tighten it a little bit. So if they type in the factorial of 250,000, it dies. Yeah. Okay. Just to be safe. Sure. Okay. So let's try this out. So if we type in -10, assertion failed, kills the program. If we type in 300,000, assertion failed. All right. So far, so good. Let's run some factorials. The factorial of 1 is 1. Factorial of 2 is 2. Factorial of 3 is 6. 2 times 3 is 6, right? Factorial of 4 is 24. Factorial of 5 is 120. Factorial of 6 is 720. Factorial of 7 is 5040, right? So, so far so good, right? Like I think we got it. I think our code's correct. I've tested 8 numbers. That is enough, right? To be confident my code is correct. Yeah? You guys think so? Are we good? All right, what higher value should I test it for? Like all the way up to, like, I don't know, 15? 16? 17? Factorial of 17 is negative 2.8 billion, right? I think that's correct. You multiply a bunch of positive numbers together, you get a negative number. It's just how math is, right? Computers don't lie to you, right? The factorial of 17 is a negative number. Of course, everybody knows this, right? There's something even more interesting here. The factorial of 16 is smaller than the factorial of 15. You guys see this? So if you take this giant number here and multiply by 16, you get a smaller number. That's just math. That's just how math works. Computers don't lie. They don't make mistakes. Okay. Let's try it. 13 is 1.9 billion. Okay. 14 is 1.2 billion. So the factorial of 14 is smaller than the factorial of 13. Interesting. Factorial of 15 is bigger. Factorial of 16 is smaller. Factorial of 17 is a negative number. Huh. All right. Well, which one of these numbers is the last one that's legitimate? Let's try 12. Yeah, that looks about right. So let's try pulling up good old Windows calculator. Let's do 13 screaming. Nope, that's not it. Let's try 12 screaming. Yep. So 12. 12. That's the biggest number we can support. So 200,000 was grossly optimistic. We can handle about 13 numbers. Right? 12 numbers, technically. So x has to be less than 13 and greater than 1. Or so what an amazing function we have here. It can compute any factorial you want as long as it's between 1 and 12. So that is... yeah, the power level exceeded 9,000 almost immediately, right? So there you go. So we have a super useful factorial function. Now, the thing is, you might be like, well, we could do that using a for loop, right? We don't need a factorial, you know? We don't need a recursive function. Here's the thing, though, like int product equals 1 for I equals 1, I is less than or equal to x, I plus plus product times equals I, return product. So this function here and this function here are equivalent. One is doing it recursively, one is doing it using a for loop. And in fact, back in the olden days, there's a programming language called Lisp, and Lisp did not have for loops. It had recursion. And so people who learned how to program on Lisp learned how to do loops using recursion first. And for them, recursion is more natural than breathing. So you can see the for loop version works fine. If we type in -1, we get 1. If we type in 17, we get the overflow still. You know, it's the same code. So this for loop here is equivalent to this recursive loop here. And that's actually something you can prove in computer science. You can actually prove that any recursive loop can be rewritten as a for loop, and pretty much vice versa. Okay, they're functionally equivalent. People tend to prefer recursion whenever they have a self-similar problem like this, because this looks like math. You know, n times n-1 factorial, right? So it looks like math. So a lot of people prefer this. I typically prefer this because I don't like stack overflowing. This code cannot stack overflow, right? If I were to type in 300,000 here, it doesn't stack overflow. That's a benefit, okay? Because it doesn't use memory every time it calls itself, right? Every time you call a function, it has to save the state of the previous function. It runs out of memory, it segfaults. For loop versions don't segfault ever, at least due to the for loop. So I prefer for loops, but there's a lot of algorithms that just look nicer when you do them recursively. So for lab time, what you're going to do, before we do lab time, somebody asked, what if we made it bigger, right? So what if we made this a long, right? That's a 64-bit integer instead of a 32-bit integer, right? So we'll make all these things longs here. Actually, I'm going to do something kind of cool here. Some auto, and that will be whatever. We'll just do it. We'll do a long one. Okay. I want to go to far down that rabbit hole. Okay. You know, I'll show you anyway. I don't care. It's probably a better way of doing it, but that's simple enough. Okay, there's a type conflict here. This is CSI 41 stuff. Basically, now we can call factorial with any type of integer type, not just integers. So if we pass in a long, it'll be a 64-bit. And so, look, we gotta get rid of the assertion. We don't know what our limits are now, right? Because we got a 64-bit integer now, and 64-bit integers can be quite big, right? Like 2 to the 64th power. That's a big number, right? That's like atoms in the universe big, right? So we should be fine, right, with a 64-bit number, right? We can go 15 and 16. Look at those numbers. They're big. How high do you guys think we should be able to go? What do you think? What's the biggest factorial do you guys think that we're going to be able to hit before we overflow this massive 64-bit number? What do you think? $21, we overflowed. So we got all the way up to 20. There we go. So by switching from a 32-bit integer to a 64-bit, we're able to go all the way up to 20 instead of 12. So fantastic. How about that? We can make it even bigger. We can make it an unsigned long. So not for negative numbers anymore. Let's see how far up this can go. 20. All right, cool. 21. No. 20, 21, 21. There we go. Handled it just fine, like a champion. 22, it overflowed, so that got us like an extra number. And that's the biggest integer type we have in the standard. So we cannot factorial for any number more than about 20 or 21. Okay. So there we go. Yeah, all the way up to 21. How amazing. Okay, so what I'd like for you to do, put this back the way it was. We'll make this a unsigned long, or if you want to save on typings, is unsigned integer 64-bit type, like that. So uint 64t is exactly the same thing as unsigned long. uint 64t. Okay. So it's just less typing. It's an unsigned 64-bit integer. And 64-bit integers are the biggest that we have in the standard, and probably the biggest we're going to have ever, due to the standards committee shooting themselves in the foot. So what I'd like for you to do is write a recursive function that uses Fibonacci, that does Fibonacci. Okay. So lab timer, write a recursive function to compute the Fibonacci sequence. Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 200 something, 224, 233, etc. And so the Fibonacci sequence is defined like this. So the Fibonacci at index x is equal to the Fibonacci at index x minus 1 plus the Fibonacci at index x minus 2, with a base case of Fibonacci of x is less than or equal to 1. Okay, so given my starter code here, I'd like for you to write a Fibonacci function that the number passed in is the index in the Fibonacci sequence. So if you pass in 0, 1, 2, 3, 4, it will return 5. If you pass in 6, it will return 13. If you pass in 8, it will return 34. If you pass in 10, it will return 89. So this number here is the index into the Fibonacci sequence, and then it computes it and returns the value back. This is the formula, okay? So each element in the Fibonacci sequence is equal to the sum of the two previous ones. So this guy is 13 because the two previous ones are 5 and 8, right? This one is 8 because the two previous ones are 3 and 5. Fibonacci sequence shows up all over the place in nature, et cetera, et cetera. And yeah, so that should be a good exercise. The only way you can learn how to do recursive functions is by doing recursive functions. That's the only way you can understand them. Or to understand recursion, you must first understand recursion. Okay? You can also Google it on Google, right? Like if you wanna understand recursion on Google, right? So if you look up recursion on Google, it's a great way of understanding it. It will say, did you mean to say recursion? You click on that. It says, did you mean to say recursion? Click on that. Did you mean to say recursion? Click on that. Okay. So again, I will give you guys 15 minutes. I will tell you it's going to be very similar to the code up on the screen here. There's going to be one word in Factorial, I think, that's going to change. Okay, and I'll give you 15 minutes to do it. Test it out, and if it's crashing, if you're segfaulting, load it up in Gdb, right? So if you like, we'll go back to the infinite loop version for a second. If you were to run this in Gdb, right, it executable segfault, and then you can backtrace, and you can see in the backtrace you've got you got problems. It's called itself all these times. Okay, so GDB, very useful stuff. All right. And you'll have to like probably adjust this, right? Okay. So if you have troubles, use it. Run it in GDB. It's good for you, like vegetables. Okay, 15 minutes starts now. All right, welcome back, everyone. I was playing some Lateralis during the break. Didn't work. Awesome. Good. So remember, the only way you can learn how to do recursion is through recursion. So, yeah, here the problem is you're using the number x and you're adding them together, but x is not the return value. X is the index in the Fibonacci sequence. So, like for this number here, x would be 0, 1, 2, 3, 4, 5, 6, 7. And so if you pass in 7, you should return 21. Okay, so basically, yeah, the problem is you're using the value. That should instead be a function call. Okay, so you're not calling yourself anywhere in here, so it's not recursive. Let's see what we got here. This is correct. Yes. You got a problem where if somebody types in a negative number, it'll loop infinitely. So make sure that that is covered. Oh, no, you got the assert here. Yeah, I guess that's fine. I guess you're good. Okay. That is A-okay. Getting an assertion error. Oh, yeah. Right. Yeah, that code's not going to work. Right, because when you do the Fibonacci of like 2, it's going to call Fibonacci of 1 and Fibonacci of 0, right? And so 0 is going to trigger the assertion every time. So that's why you're crashing. What do we got here for Voss? All right. If x is 1, return 1. Assert x is greater than 1. You probably want to put the assert above that line. Probably. I don't know. Maybe not. I don't know. So yeah, the same problem. You're going to trigger your assertion because when you do the Fibonacci of 2, you're going to recursively call down to the Fibonacci of 0, and that's going to trigger your assertion. So that's why you're not working either. Let's see what we got here. Yeah, same problem with the assert. It's going to cause issues. And Hernandez, this looks good, actually. No, not good. Because 0 should be 1. Again, you're returning 0 here. Because the 0th index is that one. So the Fibonacci of 0 is 1, right? Not 0. So that's okay problem. Otherwise, it looks pretty good. This one looks pretty good to me. I don't know why you say it only goes up to 3 properly. Oh, because yeah, you didn't recursively call here. You're adding x minus 2. This should be Fibonacci of x minus 2, not just x minus 2. Yeah, this one's wrong. The index 1 should be 1. The index 0 should be 1. And you're triple calling into Fibonacci. So yeah, this is like just adding 0 to something here. So that doesn't do anything. Let's see here. Remember, you need parentheses around if statements. Okay. So let me just show you the answer. And there we go, we're done. You know what? I should have searched and replaced those, huh? And then I could just use dot like that. See how nice that is? Oops. Did I leave an X there? No. Okay. So 1 is 1, 0 is 1, 2 is 2, 3 is 3, 4 is 5, 5 is 8, 6 is 13, 7 is 21, 8 is 34, etc., etc. Each element, the sum of the two ahead of it. So question is, how high can this one go? How high can it go? What's our limit? What do you think? For exponent, we got up to like, I don't know, 20. What's our limit here, do you think? 30, 40. Notice it's lagging. 41, 42. Why is it slowing down so much? 43 is twice as slow as 42. 42 is twice as slow as 41. 41 is twice as slow as 40. Why? Why is every higher number in Fibonacci causing 2 times the time of the previous Fibonacci call? Why is it taking twice as long every time Fibonacci goes up by 1 number? Any guesses? This is something called an exponential algorithm. An exponential algorithm is garbage running time, right? We could have done this in a for loop instantaneously, right? A for loop would be able to solve this very quickly. But for 50, it'll take actually like a long time to do. Yeah, because every time you call Fibonacci, it calls itself twice. It's like a chain reaction in a nuclear reactor, right? So when you call Fibonacci of 50, it calls Fibonacci of 49 and Fibonacci of 48. If Fibonacci of 49 calls Fibonacci of 48 and 47. If Fibonacci of 48 calls 47 and 46, and 48 and 47 and 46, and 47 calls 46 and 45, and 46 is called 4 times, calling 45 and 44. And it doubles your runtime every time the number goes up because you're calling yourself twice every time you call yourself. So this is what we call an order 2 to the n algorithm, which is exponential runtime. Okay, which is bad, super bad. Okay. All right. So do you understand recursion? You guys able to do a competency exam on it? Don't worry, there isn't one. Yeah, don't worry, there's no recursion competency exam, but it is definitely, it is something hard. I told you in computer science, you're going to have your brain hurt a number of times. You feel your brain getting stretched out of your skull. And recursion is one of those things that will do that to you. Just trying to wrap your mind around recursion takes a while to get used to. But it's something that comes up a lot because there are a lot of self-similar problems where you can solve a smaller problem to solve the bigger problem using the same algorithm. So don't worry, it's not going to be on the competency exams. I might give you a quiz question on it today or something. I don't know. But you don't have to have this mastered quite yet. But it's a thing. It's a real thing. And like I said, like a lot of people back in the day learned Lisp, and Lisp had recursion. They didn't do loops, they did recursion. So, you know. What's the correct assert statement? I don't know. I didn't have one because I just handle it, right? So if I pass in a negative number, I just return 1. And then on the upper end, it never finishes anyway, so it can't overflow. It'll just run forever. So I'm not too worried about it. All right, so that's it for today. Your next homework assignment is called Mandarin. It is a little bit of functions, a little bit of for loops. Basically, your job is just to translate numbers into Mandarin. It's not a big deal. Really, it's going to look something like this. We're going to count up to 10, starting at 1, stepping by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, sure. Right? So starting at 1, going to 10, counting by ones. If I go up to 10, starting at 1, counting by 2s, then I got 1, 3, 5, 7, 9. 1, 2, 3, 4. Right? So you have to be able to translate numbers from Arabic numerals into Mandarin up to, I think, 99,999, including 0 as well. So counting up to 0, starting at 0, counting by ones. 0 is, of course, a ling. And so the README file has a Mandarin dictionary for you to use. And basically, you're going to want to write a function that like converts like a digit into Mandarin. and figure out a for loop to kind of replicate this. And it's not bad. Like I was wanting to do something a little harder, but Min Crowley pledged your case, and he said Mandarin's a good assignment. You should have them do it. So there you go. Not too bad, I don't think. Little functionality, a little loopery, and you should be good to go. All right, I'll be due next Friday. Your Zybooks are due, as always, on Wednesday, and that's it for now. So enjoy your weekend, and I will see you guys on Monday. Peace out.